recording. And sharing the screen. We are a little bit ahead, right? So we finished the fraction, at least what I wanted to cover. So we're going to start relativity. 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 Okay. Relativity. Here you go. Let's not forget lab 1 is due. I hope to be correcting lab 1 this weekend. And that's going to be my version number 6. I will boldface it here. Let's not forget exam 2 is today, chapters 33 and 34. And going to our notes, we're going to have just insert here. Okay. Let's get okay, so that's exam 2. I'm going to highlight exam 2 here. And let's also review what we have in exam 3, right, so far. Exam 2 today. Those are the sections of exam 2. And so far we have those sections here. See? We'll be able to check our hard copy for lab 1 to see if we did it right. Okay. Yeah, let's do that. Let's see. Yeah, let's do that around 11:30, right? When we have our break, just before we have our break. Did you upload already? Did you upload your lab 1 already? Yes, okay. So I'll check it during the break, okay? Lab workbook, correct. We do not have to use the lab workbook. For which are you asking? Let's see, Joshua is asking, just confirm we do not have to use the lab workbook. Are you referring to use the lab workbook for the exam? Is that what you mean? Okay. Okay. Yeah, that's right. Exam 1, that's right. Exam 1 doesn't cover lab 1, so you don't have to for the lab reports. For lab reports. No, it's just the lab reports is just whatever I mentioned, right? You get whatever you have that in the spreadsheet, you copy and paste that to your Word document, and also you do the title page. Okay, Joshua, does it answer your question? Okay, good. So far, and for exam 3, you also have to worry about lab 1 as well. Okay. Not for exam 2, because I still didn't correct the lab report, the first lab report, but for exam 3, I need you to review how are you uploading our lab report. Well, you upload that to your group folder. Okay, you must have that link that I gave to you. You have, let's see here. Let's go to the Google folder, right? Let's go to your group folder. You prepare your spreadsheet, prepare the spreadsheet, prepare the Word document, and then you just upload it there. Let's see how we're doing here. Oh, let's see, lab report. Okay, let's see, group number 1, right? Hi, group number 1 is in there. Let's see, IME is there. Let's see. IME, okay. Okay, so do not do this title here. Just keep the same title that you had before. Okay, everybody, that goes for everybody, not just for group one. So rename it just like you had before. Let's see, rename right in here. P39, okay. L1, let's see, that's 02, okay. That's 02. Yeah, that's 02. Let's leave this way. And just leave it in this, in this format here. Okay, looks like I made it. Now I don't see lab one here for group one. Huh? Lab report must be here. Okay. Yeah, I don't, let's see, let's move that outside. Move to group one. Move, okay. And okay, that's the lab report. So yeah, I still don't see, maybe it's here. Okay, yeah, it's here. Okay, so make sure you do not rename the document, okay? Because I like to keep it in that other format in my computer. Let's see, group two. Okay, yeah, Raymond, you did good. You did great. Now you gotta do the same format, right? The same title that you use here. You use for the Word document. So here you go, rename it. Oh, no. Cancel, let's do that again. Rename it. If I get that. Yeah, it's okay to keep two different documents with the same title because they have different extensions. Okay, so make sure you use this format here, everybody, please. And let's see, group three. Yeah, group three did well. Yeah, they didn't change anything. Group four. Okay. Okay, understand that you use this format here, and that should be the Word document for the first lab report. So keep the same title as you have for the spreadsheet. If necessary, you can delete this document. Okay, if you it's just this thing is just the original data, you can delete it. Okay, group number 3, right? How are we uploading our lab report one? Okay, so all you gotta do is to click, drag, and drop, right, Alex? We practiced that at the first meeting, how to drop documents from your hard drive to the group folder. Okay. And let's see, another one. That's group 4. Let's go to group 5. Okay, group 5 has, okay, looks like they put, group 5 put a 0 instead, O instead of 0, right? Let's put a 0 there. The O is rounder than the 0. And, okay, and let's see if they did that here. Yeah, it looks like that's the one. Okay, that's the graph. That's good. So it looks like group 5 is gone. Okay, so let's some notes here, right? So that's the material for exam 2, and that's the material for exam 3. Maybe we're gonna add some chapters today. For the title of the labs, please use the following format, both for the spreadsheet and the Word document. P39L, no, in this case, it's going to be for the first lab report, right? For the first lab report, for the title of the labs, P3901, G, whatever group number you are. That's it. Whatever group, that's for the lab 1, right? Lab 2, same format. Lab 3, and so on, okay? Where XX your group number. Where XX is your 2-digit group number. Okay, any more questions? So today we'll start special relativity. Okay, and that's the point we are right now. Okay, exam 3 so far. It looks like we're going to, since we're going to start relativity, that's chapter 37. Okay, maybe I'll include relativity. I should not know. Maybe 37. Okay? Depends how far we go with relativity in this today's class. Okay, but definitely for lab 1, lab 1 will show up in exam 3. Let's put that here. Any more questions? Okay, so let's start relativity. Okay. It was at the time that physicists thought they had discovered everything that they should have they had to discover. They were very proud of their accomplishments. Newtonian mechanics was being very successful. Thermodynamics also was very successful, and as well as electricity and magnetism. But, that looks like more or less, right? But in the mid-1800s, some interesting theoretical and experimental results started to show up, start to be published, that the current theory that they judged to be so successful could not explain. Okay, so the situation was like that in the mid-1800s, in the mid to late 1800s. Physics had mechanics, right? Had been quite successful, mostly because of the Industrial Revolution, right? Think about that. It was the discovery in physics that allowed people to come up with all sorts of inventions. That period of Industrial Revolution was very similar to the period that we are going through right now, okay? People were inventing all sorts of devices, They were automating the industry, just like we're doing today. And of course, unemployment would come hand in hand with those discoveries and advances in science and technology, okay? So just more or less what we are experiencing right now. It's just amazing how fast progress is being right now. Progress has been so quick that products don't last very long in the shelves. Okay, products, they disappear in at most 7 years. Okay, they stay on the shelves for at most 7 years. That's what people usually tell me. If you invent something new, you put that in the market, that product of yours is going to become obsolete in 7 years. Then you have to reinvent something else to replace what is obsolete. So that was more or less what happened during the Industrial Revolution. At that time, we had Thomas Edison, right? Someone that everybody knows, Thomas Edison. We had people like Tesla, Nikola Tesla. We had Marconi, and the pace was going very fast. And the physicists were so proud of their accomplishments that they start declaring that there was nothing else, they had to invent, right, or discover, which would be the end of physics. If something like that were to be true, right, this would be the end of physics. But they were for a surprise. They were for a surprise, for a big surprise. So we had mechanics that you have already studied. We have thermodynamics. We had optics, right? Wave optics and geometrical optics. And you had electricity and magnetism, which had been combined into a single, electricity and magnetism, which had been combined into a single theory with the work of James Clerk Maxwell. That's what we call the unification, right? Unification of electricity and magnetism. Right now, we are trying to do the same thing with every science, every physical science, the theory of everything. They managed to do the unification of electricity and magnetism back in the 1800s. And now we are trying, to unify every theory that we have, the theory of everything. We're trying to combine all those laws into a single one, okay? We are trying to combine all the laws that I introduced into a single law that will explain everything. And so let's just review what are the laws that we have so far, right? Let's see. I like to call it the 2 laws of mechanics, the 2 laws of motion, not the 3 laws of motion, but the 2 laws of motion. The first law of motion is just a special, the first law of motion is just a special case of the second law. Okay? In mechanics, we have the 2 laws of motion plus the law of gravity, the gravitational law. Gravitational law. Okay? That's what we have in mechanics. In thermodynamics, we have the zeros, the zero law, the first law, the second, and the third law. That's what we have in electricity and magnetism, ENEMA, the Maxwell's equations. Maxwell's equations for Maxwell's equations. And in optics, we have the principle of least time. Of least time. And by the way, the optics is nothing but a subset of electricity and magnetism, okay? Remember that propagation of light is made of electric and magnetic physics and magnetic fields. Because of that, optics is a subset of electricity and magnetism. So we can go ahead and take it out. The principle of least time applies to geometrical optics, right? Which, by the way, is just a corollary to wave optics, which is a corollary to wave optics. Everything that wave optics, everything that geometrical optics explain, wave optics explain as well. So I'm going to put optics right in here as it is a subset of electricity and magnetism. That was the state of physics. But scientists were for a surprise. But scientists were for a surprise. Okay. First, the first surprise, had to do with the Galilean transformations, which is nothing but, what we studied, relative motion, right? The concept of relative motion, we studied that in physics 37. And I'm going to go back to this concept of relative motion because it's going to be important in relativity. Do you see here? Relative motion, okay? And then you also have special theory of relativity. There's no coincidence that we have relativity here and relative motion here, okay? That's no coincidence. There's a direct connection between the special theory of relativity of Einstein and the Galilean transformation that Galileo came about. Galileo proposed at his time to explain relative motion. We are talking about, think about that, from the time of Galileo to the time of Einstein, 1900, right? And Einstein was around the late 1800s and early 1900s. And what about Galileo? Galileo was, Galileo Galilei. Let's see here. Born in 1564 and died in 1642. So it was in the 1500s and the 1600s. Galileo lived during the great navigations, right? So we are talking about 300 years. Almost 300 years. So Einstein made this connection with the theory that Galileo proposed with his own theory. And because of that, we are going to review it all over again. So you can refresh your memory about the concepts of relative motion. Okay. The lines, relativity, special relativity. It is special relativity because it deals with uniform motion. That's why it's called a special relativity. Only objects moving with constant velocity or inertial frames of reference, okay? So let's review Galilean transformations before we get into Einstein's special relativity. So we have a referential A with an x-axis and a y-axis. I label referential A right in here next to the y-axis. Okay, that's our referential. And then we have this point P along the x-axis of referential A. This point P can be denoted as with a coordinate axis at xPA. Let's not forget too that what I missed here is that we must have also the origin of my coordinate axis. I'm gonna put it origin for O. And I don't want that to be italicized. Okay, origin of A. And that's gonna go on every other slide that comes about, okay? So we have this point P, the same notation that I have used in physics 37. Okay, and this point P has a coordinate x of P with respect to A. That's what this notation means, okay? Position of P with respect to referential A. That's what it's all about. It's very intuitive notation and it's very useful too. And now I can describe the position of P in terms of a vector. Vector of P with respect to A, with respect to the origin of A. That's what it means. And then we add a referential B. If you want to do relative motion, if you want to work with relative motion, it's going to be motion with relation with respect to two referentials, one referential with respect to another. Okay, so I'm adding the second referential that you see. Then, according to referential B, this point P has a different coordinate or a vector position. Okay, vector position of P with respect to referential B. And, oh, don't forget, right? Something else I'm forgetting here. I have also to add, my origin for B as well. Origin for A, origin for B. Well, it's going to come in the next slide. So I do not overwhelm you with notation. Here you go. Now, I'll call this origin prime to differentiate from the origin of the other one. And now that I have those two origins here, okay. So this point P can be referred with respect, can be referenced with respect to referential B as well. And that's going to be the vector position of point P with respect to B. Right? And we must have the vector position of the referential B, the origin of referential B, with respect to referential A. See how the notation goes? Whatever goes at the end here is making reference to the referential. Here I'm making reference to the referential B. Here I'm making reference to the referential A and referential A as well. And according to this notation here, I did the one-dimensional, but we can do two-dimensional as well and three-dimensional as well. What we end up getting? We end up getting the following notation. Okay. According to the Galilean transformation, we have the following relation between the two referentials, A and B. So here we go. I'm going to do it in vector notation first. Position of point P with respect to point B. Let's do it with respect to referential A first, and then we change it. And I'm going to change the color as well. Good. Is going to be equal to the position of point P with respect referential B plus position of referential B with respect to referential A. It's a very intuitive notation. Why is it a very intuitive notation? Because we have P here, and we have P here. We have A here, and I'm going to put both facing red. And we have A here in the other term on the right side. It's not difficult to memorize. And finally, this B here, it is as though as this B is canceling out with this other B. Okay, and I'm gonna put that in blue color, blue bold color. Can you see that? The B right in here, PA, and you can use this notation for any other referential. Okay, here you go. For any transformation too. So now I'm going to rewrite that in the one-dimensional case. X of P with respect to A is X of P with respect to B, and X of B with respect to A. Okay, let's take a look at our drawings side by side. And let's see if this notation is exactly what is illustrated there. That's okay. X of P with respect to A is X of P with respect to B plus X of B with respect to A. Okay. And we can go the other way too. And by the way, there's one more thing here I'm gonna put it. Here you go. Then we can say that referential B is moving with respect to referential A from the left to the right. If we do that, we can rewrite our equations, our transformations, as being, X of B with respect to A becomes X of F, becomes V of B with respect to A times T. Okay. This V of B with respect to A can be either positive or negative. You can have an implicit positive or negative sign there in this notation. Okay. And by the way, this notation works in the other way as well. Okay. Here you go. Instead of taking all this with respect to referential A, we can take that with respect to referential B. The only thing that's going to change is the color of the referential B and the referential A. Here, like that. It works this way as well. PB PB. AA, it is as though as AA cancels out here. If we do that for the one-dimensional case, so Einstein's theory of relativity is nothing but an elaboration of the Galilean transformations that we are doing here, but with far more profound consequences. Far more profound consequences. And here go again, we can V of A with respect to B times T. And like I said, this V here can be either positive or negative. The notation is no different than the other one. These are the Galilean transformations. I'm going to place them side by side. And I'm doing just for the one-dimensional case. Okay? By the way, V, this notation has a very nice mathematical property. And what is this mathematical property of this notation? Is that if you invert the subscripts, you must also apply a negative sign there. Okay? And I'm going to illustrate what V of A with respect to B is all about, right? So here we go. I am denoting here that X of B with respect to A is VBAT. And then there's nothing new here, right? The only thing that I gotta do is add the origin of the two referentials. This one here, right? And what do I have to do now? I have to do the other transformation, right? We do not need that. Here you go. Here's the other transformation. And I'm going to change. Okay. Here's the other transformation. So go ahead, think a little bit about that. I'm going to give you a little 5 minutes before we return to that. Look at this notation. I'm going to put, look at this one first, that's easiest, right? And let's take a 5 minutes break while you look at that. And when I come back, we go for, I'll take attendance and we have our 15-minute break, okay? So look carefully at that. So when I say that Einstein's theory of relativity is closely related to the Galilean transformation, this one that I spelled out for you here, I'm not lying, okay? It's one of the most basic, what we have here is the most basic equations of physics. It's nothing but relative motion, something that we studied in mechanics. But of course, it's going to be done in a relativity a little more sophisticated than that. If it came 300 years later, it had to be more sophisticated. Okay. And what was the problem? So at that time, even though physicists thought, at the time thought they had discovered everything that they should have discovered, everything they were supposed to discover. And we're saying the same thing today, okay? With this standard model, people are saying that we have already done everything that we could have done in physics. So most likely they are making the same mistakes that the other scientists 120 years later were making, 170 years later they were making. Some odd, not just experimental results, but also theoretical results. Some other experimental and theoretical results were showing up in physics, which did not have a proper explanation within the realm, we call it the realm of classical mechanics. And classical mechanics slash physics is the theory that was completed by the mid-1800s. Electricity and magnetism is considered part of classical mechanics, thermodynamics, E&M, okay? Everything else that came up after, at the beginning of the 1900s, at the beginning of the 20th century, is called modern physics. Every classical physics, what lasted the theory, that was the theories, right? That were formulated until the 1850s, until mid 1800s, mid and late 1800s. Okay, everything else that came up, everything else that came up after the beginning of the 20th century, we call modern physics. So we have classical physics and then we have modern physics. One of them was the theory of relativity. So let's see what was the problem that the scientists were facing. First, you already know, we had the results of Michelson and Morley experiments. The ether was a fundamental piece in classical mechanics. The ether was a fundamental concept in classical mechanics. And yet, the Michelson and Morley experiment put a question mark in its existence. So that was problematic for physics. This implied two things. One, there was no absolute frame of reference, which would be the ether frame of reference. And two, light did not require a physical medium to propagate. Physicists were stuck on this idea that any wave had to have a medium to propagate. that and these experiments start to shake this belief among physicists. You know, that was part of the Mikeson-Morley experiment. Okay, the Mikeson-Morley experiment was part of what we call the shift, part of what we call the shift in the thinking of the time. They have to start thinking in a different way. Physicists have to start to think in a different way in order to understand what is going on. They were tied to something that was not a proper idea. It's like you believe in a lie and you live by that lie, right? When you live by that lie, eventually that lie is gonna catch you. Sometimes lies are good to progress in your knowledge, right? But then they have limitations, right? Did not require a physical medium to propagate. That was one problem in physics. Okay, and then there was something else with the unification, too. With the unification of electricity and magnetism, come on. People discovered a new transformation that was rather similar to the Galilean transformation, but not quite the same. Not quite the same. Today we call this transformation. Today we call these transformations, right? Because it's more than one. Transformations, the Lorentz transformation. If the Galilean transformation was that one that you saw here, I'll get this one here. If the Galilean transformation was something like that, the Lorentz transformation was something else. I'm going to just concentrate on one of the transformations, okay? The Lorentz transformation was something quite similar to that, but not completely. It had a multiplicative factor. They attribute that transformation to Lorentz. But when you look at the books, okay, they mention someone else where this gamma factor, okay? This gamma factor was given by the following: 1 divided by 1 minus velocity of referential B with respect to velocity of with respect to referential A. By the way, this term was squared, divided by the speed of the light. Okay, and by the way, there is also a square root term here. This transformation here, reduces to the Galilean transformation. Note that if VBA, right? Note that if dBA is much less than C, the Lorentz transformation reduces to the Galilean transformation, right? Note see that. And that was the state of affair that Einstein, not just Einstein, but physicists were facing at the time. Einstein was aware of this transformation, but he was not aware of the Michelson and Morley experiments. Okay. When Michelson-Morley published that, when Michelson-Morley published their experiments, their experimental results, someone else, Fitzgerald, his name was Fitzgerald. Remember the video of yesterday, right? Claimed that one of the arms of Michelson interferometer, right, seemed to be contracting. But it was Fitzgerald who was saying that. It was not Lorentz. Fitzgerald was kind of a non-physicist at the time. So when he came up with this idea, people started scoffing at his suggestion, right? Until Lorentz came about and said, look, this transformation here allows for the Fitzgerald contraction. That's when the physicists start to pay more attention, because Lorentz was someone that was seen as a much more respectable scientist, okay? And then came Einstein, okay? And then came Einstein. That was the mess that physicists were caught in at the time. They couldn't make sense of all those discrepancies, those two discrepancies. The Michelson-Morley experiment and the Lorentz transformation, including the Lorentz-Fitzgerald contraction. Even though it was Fitzgerald who first suggested that, at the end, people start calling the Lorentz-Fitzgerald contraction. Okay, what we call today, think about that, objects contracting as they move in space. What we call today the Lorentz-Fitzgerald contraction. I'm gonna put that here. That's not fair, right? It was Fitzgerald who first suggested, and yet the guy and yet he doesn't have his name in front of this term, right? It's just supposed to be the Fitzgerald-Lorentz contraction and not the Lorentz-Fitzgerald contraction. So how Einstein solved this dilemma? Okay. How Einstein solved this dilemma, right? But this dilemma also, here you go. This dilemma also suggested that either the Maxwell's equations were incorrect or incomplete, right? One, either the Maxwell's equations were incorrect or incomplete, or two, the Galilean transformations were incorrect / incomplete. Not incorrect because it has been very successful, okay? Theories in physics are not incorrect, okay? theories in physics that fail, we say that they are incomplete. We say they are incomplete because they are very successful in predicting how the universe works. Okay? But they are incomplete because they are successful up to a certain point. After that point, then we have to add something to that theory to make it compliant with the behavior of the universe. Let's see here. How are we? It's not VP of B. Okay, where is that? Just now I saw your message here. VP of B is 8:40. Wow, 20 minutes ago. Okay, Raymond, where is that VP of B that you're mentioning? The drawings or in the equations? Is Raymond still there? Raymond left a message here that I just saw it. That was from like 15 minutes ago. Yeah, I know. But you're referring to the drawings or the slides or it was about the velocity vector in the slide. Okay, let's take a look. Slide, here we go. VP of B is this one here. Let's see here. Originating from the referential YB, right? No, it's not VP of B. VP of B is the other. Yeah, don't forget, P is the point, right? Is the point. So here you go. We have this point P here. That is in this referential. And then what we're doing, we're measuring the position of this point P with respect to different referentials. I guess that what you are confusing is the other equation that I didn't write that down, okay? VB of A, right? VB of A, VA of B. Okay, so I don't see any mistakes here, right? Okay, but I believe that what you're confusing is with this equation here that we also see in physics, right? I didn't go for this equation yet. V, right? Velocity of P with respect to A is velocity of V with respect to B, and the velocity of B with respect to A. Okay, that's another equation of relative motion. And how do we get that? We get that just by differentiating this equation here. Not this equation, sorry, this equation here. Okay? Maybe that's what you are mixing up with, okay? And then this format, remains the same. Because there is not just for the position, right? There is also an equation like that for the velocity, for the relative velocity, and the relative acceleration, okay? So here we go. I'm gonna put B here, VP of A. So it's two referentials and one particle, right? And we're describing the motion of that particle with respect to different referentials. Okay, and then we have this other set here that deals with the acceleration. I didn't go that far because we didn't have to. I'm just dealing with the position of the particle, right? A. I'm going to copy and paste it here. I'm going to copy and paste here. And then I have to put A here. Make sense? So most likely that's what you are mixing up with cancel. So I'm going to put all those sets of equations right in here. Students coming. And the P of B, let's see, R P of B, right? P of A. And then A of B. Like that. Okay? They all have the same format, whether it's the position, velocity, or acceleration. Okay, so that's what the situation was. And let's see how Einstein solved this dilemma. Okay? Or there's another possibility too, or three, it was something else. Just something else. Either two were incorrect. Okay, it was something else. Or maybe both of them were incorrect too. That was another possibility. The most obvious, let's say, answer would be that the Galilean transformations were incorrect. Because Maxwell's equations were very successful, and so was the Galilean transformation, right? But let's see what ended up happening, right? And how Einstein solved this dilemma. This dilemma, here you go, was solved by Einstein by proposing one new law, one new postulate or law, and by reminding scientists of an old postulate. Okay. So it's only two postulates, only two laws. Relativity has only two laws. So what are the postulates of relativity? Huh? The first one, you gotta memorize that. First postulate, first law. It's called the principle of relativity. The laws of physics must be the same in all inertial frames of reference. Okay? Just like Newton's law, right? Just like Newton's law. Just like Newton's law. Break down, right? Break down in a non-inertial. They don't break down, just like Newton's law need an adjustment. Adjustment in a non-inertial frame of reference. Okay. Every law of physics must also obey this principle of relativity. Nothing new here, right? In mechanics, right? If we had no inertial frame of reference, we had to adjust Newton's second law of motion. Okay, that's so remember, the same in all inertial frames of reference. If the frame is not inertial, if the frame is accelerated, you have to be careful how you apply your laws of physics. That's just a reminder. And then we have the second law. That was surprising. No scientist could believe that. Even today is difficult for us to grasp, especially if you are exposed to it for the first time. Okay, second law. The speed of light in vacuum is the same, 300,000 kilometers per second, in all inertial frames of reference, regardless the velocity of the observer or the velocity of the source emitting the light. That's something you have to memorize and understand because it has very important consequences. And I'm going to emphasize it. Read it, stop, read it, and try to understand what it means. Try to understand what it means actually, and try to visualize how you can explain that in a graphical sense, in an illustration, in terms of an illustration, okay? And that's exactly what I'm gonna do that before we gonna go into our break. So here you go. Measuring the speed of the light in the same frame of reference. Okay, so you have here your frame of reference. It's an inertial frame of reference. Reference A, referential A. Okay, we have a laser source here. And they are going to perform an experiment in this frame of reference A. You put your detector, in that same frame of reference. The light source is at rest with respect to your detector. And this detector is going to measure the speed of light. There are ways of doing that. One way to do that is to use the Michelson-Morley interferometer, okay? That's one way to do that. So you go ahead, perform the experiment, and both devices are at rest with respect to each other, right? Laser beam. And what you get 300,000 kilometers per second, okay? And now we are going to repeat the experiment in a different way. That's the type of experiment that has been done over and over again. And that's exactly what Michelson and Morley were doing with the interferometer at the time. That's one of the things, right, that they're doing with the interferometer at the time. Okay, now we are going to repeat the experiment in different frames of reference. But the frames of reference is still inertial, different inertial frames of reference. And what we're going to do, referential A, laser source. Referential B, now referential B is moving towards referential A. Velocity of B with respect to A. And then what we're going to do, we're going to attach our detector to referential B. Now the detector is moving towards the laser source. What do you think is going to be the speed of the light that this detector, that this interferometer is going to measure? Okay? Detector to measure the speed of light. You go ahead, Both devices are at rest with respect to their respective frames of reference, right? They're not at rest with respect to each other. They're at rest with respect to their respective frames of reference. The laser is at rest with respect to referential A. The detector is at rest with respect to referential B. But the referential B is not at rest with respect to referential A. And then what Einstein's second postulate mean? It means that this detector is going to measure 300,000 kilometers per second for the light, the speed of the light, and not 300,000 kilometers per second plus VBA. That was the failure of the Galilean transformation. The Galilean transformation would expect that the velocity of the light measured by this detector would be 300,000 kilometers per second plus the speed of its referential. And that's an idea that completely escaped our understanding, because we don't live in a universe, we don't live in a universe, that's right, that is easy to travel at a velocity that's very high, that's comparable to the speed of the light, okay? So that's the consequence of Einstein's second postulate. That's what it means. And it doesn't matter how you commute that. It doesn't matter if you move your referential B away from the laser. It's still going to measure 300,000 kilometers per second. Not 300,000 kilometers per second minus VBA. No. See here, the velocity here? Compare this one with this one, right? Moving away. And even if B is at rest with respect to us, right? And A is moving towards B, you still get 300,000 kilometers per second. A is moving away from B, it's still 300,000 kilometers per second. That was, the idea that Einstein had that people couldn't believe, okay? They couldn't believe not because the velocity of the light was constant in the referential, with respect to referential, but because of the consequences of this idea. This idea, this very simple idea, had very important fundamental consequences. One of the consequences was exactly what Fitzgerald mentioned, that the arm of the interferometer was shrinking. That's why Michelson-Morley couldn't see any relative motion with respect to the ether. Okay? Just with Einstein's second postulate, he was able to grasp every odd phenomenon that the scientists were observing at that time. Okay? And that's what we're going to do after our first break, okay? But before okay, so now that you have to have in mind all possible permutations of relative motion of the detector and the laser source, right? We did all of that, one-dimensional, but we did it at least everything in one dimension. Let's see this one here. Okay, that's another illustration of the same thing, right? So here you go. Here we have referentials A and B. They're coinciding with each other. Referential B is the red one. Referential A is the black one. And then what do we do? We have this particle, photon, light particle or photon that's traveling to the right, right? That's the velocity of point P with respect to point A, this velocity of C. And velocity of the point P, which again is the photon, with respect to referential B is also C, okay? So here you go. As the referential B moves away from referential A, and the particle is moving faster than referential B, That's why it's ahead, right? They keep on doing the measuring the velocity of the photon, both A and B, and it still is going to be c 300,000 kilometers per second. Okay, and then we can do examples with an airplane. Okay, but before we get there, let's start doing something else. That's okay. We're going to start with the light clock now. And with the light clock, I'm going to prove to you the phenomenon of time dilation, okay? That's the next step here. So we established that the velocity of the light is always the same, no matter how one inertial referential, right? One inertial referential is moving with respect to another one. Now we are going to do the light clock. Okay, think about a clock that has this photon that's made of light, okay? Think about the clock that uses the motion of light to keep time. The light clock, okay? A timepiece that uses the motion of the light of a photon, the motion of a photon to keep time. And the way it works, the light clock is like that. Here you go, we have the referential A. Here we have an observer in referential A. This one, what you see here is the eyeball of the observer in referential A, okay? And we have this referential B that's moving to the right along the x-axis of referential A. And here you go. In referential A, we also have an observer. And on the top of that, we have this light clock. Okay, here the observer, and in the next slide, you're going to see the light clock. How the light clock behaves, right? Try to imagine that. Those are thought experiments that physicists do all the time to imagine what happens in real life if you don't have the proper equipment to perform the experiment, right? So try to use your imagination to visualize this light clock. This light clock has two mirrors, one at the bottom and the other at the top. And somehow you put a photon particle here, and this particle moves up and down, okay? Up and down. It's being reflected over and over again. Every time it reflected in one of the mirrors is a tick, and the other mirror is a tock, tick tock, okay? We have a very good animation there in the mechanical universe that talks about the light clock. Let's do that. Let's take a look at that. Mechanical universe. The light clock. Let's see if they have light clock there. Lorentz transformations. Special relativity. Which video is this one? Current 42. Let's take a look. Mechanical universe, Wikipedia. They have an entry for the mechanical universe on their Wikipedia, but for some reason my Wikipedia is not coming here for some reason. Okay. Okay, let's try the mechanical universe again. I want to see the episodes, the mechanical universe animated series. Okay, 1985. That's how old this series is. Special relativity. The Lorentz transformation, and then we have the special velocity and time, 43, 42. Okay, let's take a look at this one. That's not the Michelson-Morley experiment that we saw yesterday, right? This one, let me pause here, make sure. Yeah, Michelson-Morley experiment was 41. Episode. We want the 42. Okay, mechanical universe. 40. Let's 41, episode 40. Let's see here. Episode 40 is optics. Okay, so 41 should be the Michelson-Morley experiment that we saw before. So let's take a look at 42. 42 is the Lorentz transformation. So that's the one we want. I'm gonna put a link for the for this episode of the mechanical universe. Link for the mechanical universe, the Lorentz transformation. We have 40.
Last time, I told you the conventional history of relativity. There was the theory of the ether, and then the Michelson-Morley experiment showed that it was wrong, and then Albert Einstein produced the theory of relativity. As I told you then, that story is logically correct, but not historically correct. Well, what is the real story? I'll get back to that in a little while. First of all, I would like to tell you about a part of the theory which is still called the Lorentz transformation.
In the Lorentz transformation, there is above all the speed of light, the speed that sprang from Maxwell's equations, the 300,000 kilometers per second that Michelson measured with landmark accuracy, the speed which is essential in modern physics and vital to understanding the universe as it really is. And at the end of the 19th century, when Lorentz derived his transformation equations, came to speed, the most moving human experience was provided by train. The automobile, which would eventually outpace the train, wasn't quite in gear, and air travel was barely off the ground. Big or small, sophisticated or child's play, trains were the very image of speed. And in fact, the only thing on Earth that moved people faster was the Earth itself. Orbiting the sun at 108,000 kilometers per hour, the inhabitants of the planet may not be aware of the speed, but speed it is. And to physicists at the turn of the century, it was speed relative to the ether. Since the time of Aristotle, the ether was believed to be the very stuff of which the heavens themselves were made. That concept remained mere speculation until two Americans set out to prove once and for all that what was then called the luminiferous ether did in fact exist. They were Albert A. Michelson and Edward Morley, and their goal was to detect motion through the ether by measuring its effects on the speed of light. In one attempt after another, with the most sensitive experimental device ever constructed, they found exactly what they weren't looking for. The interferometer showed that regardless of the motion of the observer, the speed of light is the same. For Michelson and Morley, this was bad news, and it traveled fast as a boat could carry it, to Ireland. There, physicist G.F. Fitzgerald, an early champion of Maxwell's electromagnetic theory of light, examined Michelson's otherwise disappointing result. Fitzgerald's explanation was that in its motion through the ether, one arm of the interferometer was contracted by a fraction of its length, which was just the right amount to allow the two light beams to arrive simultaneously. Immediately, most scientists scoffed at the idea. However, when Hendrik Lorentz arrived at the same idea, no one was laughing. Not only was he the world's expert on Maxwell's electromagnetic theory, but Lorentz gave a tangible explanation for the contraction phenomenon. He thought it had to be a property of the electron, whose existence had just been confirmed by J.J. Thomson and his colleagues in England. It seemed that in electrons, they found the inner parts of atoms, the ultimate constituents of matter. But they hadn't discovered all the things that electrons actually do. One possibility, Lorentz believed, is that an electron will contract in the direction of motion. If that were true, and since everything is composed of electrons, then an interferometer would contract in the direction of motion. So would a ruler, and so would a locomotive. While length contraction took care of the Michelson-Morley experiment, Lorentz knew more was needed to explain all the experiments that had failed to detect motion through the ether. Since he still believed in the ether and the fact that the Earth moved through it, he felt that somehow the electron must be responsible for this amazing fact about light. Regardless of the speed with which they themselves are moving, all observers measure the same speed of light. Certainly, other speeds, say the speed of a moving train, aren't the same to all observers. To an observer on a platform, for example, this train's passing at a good clip. But to someone on the train's speed seems to be zero, and the ground outside seems to be moving instead. Therefore, as Galileo was well aware in the Renaissance, and as this fellow knows today, the speed of an object depends on the observer's speed. But Lorentz said that perceptions of light waves would be radically different. He suggested that even someone traveling at nearly the speed of light would still observe light moving at 300,000 kilometers per second. How could that be? Consider two observers in relative motion. In this case, Albert and Henry, just for the sake of argument. At the exact place and time they pass each other, they observe a flash of light. A sphere of light expands outward from that point. Since each measures the speed of light relative to himself, each believes correctly that he is always at the center of that expanding sphere, even though they themselves move farther and farther apart.
What you see here is an illustration of Einstein's second postulate, okay? Let's play it again.
Just for the sake of argument.
Okay, here is the camera is in the referential of Einstein, right? Or referential A. And Einstein is observing
place and time they pass each other.
The flash of light.
They observe a flash of light.
And he sees that the sphere is centered around him.
A sphere of light expands outward from that point.
But now here's in the referential of Hendrik Lorentz. And he's going to see the same thing. He's going to measure exactly the same thing that Einstein measured, that the flash of light is centered at him, not at Einstein.
Since each measures the speed of light relative to himself, each believes correctly that he is always at the center of that expanding sphere, even though they themselves move farther and farther apart. How can two people in different places both be at the center of the same sphere? To confirm his perception, each sets up light detectors an equal distance apart. However, while Albert's detectors register the light arriving simultaneously, he believes the light strikes Henry's detectors at two different times. Meanwhile, Henry sees the same thing in reverse. They agree on the speed of light, but they disagree on whether events happen simultaneously or at different times. This is not semantics, nor a petty debate. It means that time, as well as distance, has to be affected by motion. However, as profound as this was, the French mathematician Henri Poincaré objected to the limited nature of Lorentz's explanation. What was needed, he said, was a new fundamental law of physics, the principle of relativity, according to which the laws of physical phenomena should be the same, whether for an observer fixed or for an observer carried along in a uniform movement of translation. In other words, as Galileo had suggested, one state of uniform motion is as good as any other. After all, this idea was the basis of Galileo's reasoning and the law of inertia almost 300 years earlier. But Poincaré was suggesting that the idea of Galilean relativity should be generalized to include all physical phenomena, including light. For example, an observer could not determine whether he was in motion by measuring the speed of light, since that speed is the same for all observers. And that meant age-old notions about time and space had to change. And though Poincaré himself shied away from examining the consequences, Lorentz developed the equations needed to show precisely how much rulers would have to contract and clocks would have to slow down when they were in motion.
Here you go. Here's
The essence of his reason.
this one is the light clock. Okay. Every time that the photon is hitting reflected by a mirror, there are two mirrors, right? One here, one at the bottom, the other at the top. You hear a tick and a tock.
Can be seen with the aid of the simplest possible clock. Two mirrors a fixed distance apart, with a light beam bouncing back and forth between them. Each bounce of the beam is a tick or a tock of the timepiece. To Henry, his clock is stationary and altogether ordinary. But for Albert, that clock is moving. And between tick and tock, he sees the light beam trace a diagonal path, which means it's traveling a longer distance. But the speed of light is the same for all observers. So the light must take a longer time to travel the longer distance. Therefore, Albert believes the moving clock runs slow. But how slow?
Relativity of time is derived from the right triangle formed by the distances traveled. The Pythagorean theorem shows that the path of the moving light is longer than the distance between mirrors. By the factor 1 over the square root of 1 minus v squared over c squared. This factor occurs so often in relativity that it is given its own symbol, the Greek letter gamma.
So to an observer at rest, a moving light clock seems to be running too slowly by the factor gamma. A ruler, or anything else in motion, also seems contracted by that same factor, and it's called the Fitzgerald contraction. For speeds much less than the speed of light, gamma isn't very large. For example, the Earth, in its headlong dash around the sun, is shortened by no more than the length of one blade of grass. As for speed on the Earth, while Lorentz was busy developing his theory, the steam locomotive barrier of 100 miles per hour was broken. At that speed, the entire train is shortened by less than the width of one atom of the paint on its engine. And Lorentz himself didn't move slowly. He was the international physicist. Young physicists from around the world attended his lectures at the University of Leiden in the Netherlands, where he'd been a professor for a quarter of a century. Among those who came to Leiden was Albert Einstein. Over the years, Lorentz would have an enormous profession.
This one here must be Marie Curie. Einstein here, Lorentz here. This one looks like Max Planck. We're going to talk about him.
And personal influence on Einstein. Just before his death, Einstein said, "I have admired and loved Lorentz perhaps more than anyone else I have ever known." But it was Lorentz's work as a theoretical physicist that went beyond his privileged circle of friends and traveled freely through time and space. Knowing he was on the right track, Lorentz pursued the consequences as far as he could. If moving things appear shorter and moving clocks run slower, then how can two people moving in relation to each other agree on a consistent description of where and when some event happened? To answer that, what's needed is a set of equations to replace the old Galilean transformations. These equations weren't hard to find, but some of their implications were hard to believe.
In Galilean relativity, the position of a point x prime in a moving frame is related to its coordinate in a fixed frame by x minus vt. Lorentz found that for the new relativity, this must be multiplied by the factor gamma. That's the equation along the direction of motion. In directions perpendicular to the motion, distances are the same in both frames.
And as for time, although clocks can be synchronized in any one frame, their readings in another frame may depend on where they are.
The time in the moving frame is gamma times the quantity t minus vx over c squared.
Together, these equations are the Lorentz transformation. They express the mathematical essence of the special.
Now let's take a quick look what's happening here, right? This position here is now is a function not only of the other position, but it's also a function of time and the velocity. Okay, so think about that. When we started our course in physics, we said that there were 7 basic quantities, right? One of them was the length, the other one was time. But when we said that, we implicitly stated that length and time are independent of each other. Okay, Einstein found otherwise. Einstein's finding here that position, which is related to length, depends not only the velocity, but depends on time as well. So now we need a completely new way of formulating physics. That's how, revolutionary relativity was in physics. We had everything organized in terms of the 7 basic quantities that are supposed to be independent of each other. And then comes Einstein and before him Lorentz, right? And says, hey, wait a minute, length is not an independent quantity. Length is a quantity that depends on the velocity, at least the velocity, right? And now we are at the point that we need to reformulate our core concepts of physics. Okay, and relativity does that. If you take a more advanced course, relativity does that for you.
Theory of relativity. Their readings in another frame may depend on where they are.
The time in the moving frame is gamma times the quantity t minus vx over c squared.
Together, these equations are the Lorentz transformations. They express the mathematical essence of the special theory of relativity. The Lorentz transformation slows time and contracts distances in a moving frame, no matter which frame is taken to be moving. The observer in the moving frame thinks he's at rest and that the other frame is really moving. But these equations do more than that. They actually join time and space together. When an event occurred has no meaning without saying where it occurred. For the Netherlands. Lorentz publishes the definitive version of his electron theory. It contains the essential equations of the theory of relativity. But Albert Einstein has not yet been heard from, which has caused some to say that history has given him more credit.
Okay, do you see what he said? Lorentz himself published the Lorentz transformation, which contains the essence of relativity, right? But Lorentz himself, he did not arrived at those equations from first principles. That's the difference between Einstein and Lorentz. Lorentz thought that the length contraction was due to a property of the electron. That was the postulate of Lorentz, right? When in reality, the length contraction was due to the velocity of the light that was the same in every referential. That was the key concept that Lorentz could not discover. It took Einstein to discover that. Let's play it again.
In time and space together. When an event occurred has no meaning without saying where it occurred. (1904), the Netherlands. Lorentz publishes the definitive version of his electron theory. It contains the essential equations of the theory of relativity. But Albert Einstein has not yet been heard from, which has caused some to say that history has given him more credit than he deserved. 1905, Bern, Switzerland. Einstein, a young physics student supporting himself as a patent clerk, finds himself disturbed by seeming inconsistencies at the very core of physics. Can inertia and the laws of mechanics be made consistent with Maxwell's theory of optics and electromagnetism? Einstein decides that they must, even if that means giving up not only the ether, but the traditional meanings of time and space. He sets forth two fundamental postulates. The first is Poincaré's relativity principle. The laws of physics are the same for all inertial frames. His second postulate states that the speed of light is the same for all observers. He simply assumes the phenomenon that Lorentz has been struggling to explain. From these two postulates alone, Einstein deduces exactly the same equations Lorentz discovered earlier. But now they have a very different meaning. The fundamental concepts of space and time have become intertwined. The essence of the idea can be understood by visualizing time as if it were another dimension. Albert, standing still in space, flows through time, so that a vertical line represents a fixed point, x equals 0, in his reference frame at different times. While a horizontal cross-section represents simultaneous times in different places. On the other hand, someone in motion, Galileo, for example, traces an oblique path. So while what Albert thinks of as a fixed point makes a vertical line, Galileo's idea of nothing happening appears as a tilted line at x prime equals 0, or anywhere else in his frame. But of course, if Galileo had drawn the picture, his line for standing still would be vertical, and Albert's would be tilted backward. The same idea can be used to show the relativity of time. When Henry and Albert observed the same expanding light sphere, it reaches their detectors at definite points in time and space. These are called events. Meanwhile, the light itself traces out a cone. To Albert, events on the horizontal cross-section are simultaneous. For him, one of Henry's detectors flashes first. Then both of his own flash simultaneously. And finally, Henry's flashes. So he thinks these two events are simultaneous. But Henry thinks these two events are simultaneous. So not only are Henry's lines of constant position tilted, but so are his lines of simultaneous time. For Henry, simultaneous events take place everywhere on a tilted cross-section. So he thinks one of Albert's signals goes first, then both of his, then Albert's other signal. Of course, if Henry were drawing the picture, he would draw his lines of constant place and constant time perpendicular to each other. Amazingly, that wouldn't change the light cone at all. This way of looking at things is called a space-time diagram, and many of the strange effects of relativity can be visualized this way. For example, Albert thinks that Henry's ruler isn't quite a meter long, while Henry, seeing Albert speed by, thinks Albert's ruler is short. On the space-time diagram, Albert measures lengths on his space axis, where Henry's ruler is shorter. But on Henry's axis, the situation is reversed, and Albert's ruler is shorter. And what about the mystery of the clocks? How can each think the other's clock is slow? On the space-time diagram, just follow the bouncing light beams. On Albert's time axis, Henry's ticks are farther apart than his own. But on Henry's time axis, Albert's ticks are farther apart, no matter how he looks at it. Actually, there's more than one way to look at the Lorentz transformation itself. While it was first derived by Lorentz, Einstein arrived at the same equations, but from a completely different direction. Lorentz used the equations to explain the Michelson-Morley experiment, while Einstein's goal was to establish relativity as a fundamental and universal principle for all of physics. For Lorentz, the constant speed of light for all observers was a mere appearance. For Einstein, this constant speed was a principle from which all else should be derived. Lorentz was perhaps the last great classical physicist, but the equations that bear his name are at the heart of relativity and the future it created.
In any case, there are two completely independent histories of the theory of relativity. One of them goes this way. There was the ether theory, and then the Michelson-Morley experiment and other experiments failed to detect its existence. And then Poincaré and Lorentz, with great difficulty, produced the formulas that were necessary to explain the results of those experiments. And then, completely separately and independently, young Albert Einstein was worried about a deep problem having to do with the nature of light and electricity, and he decided that this was the way the world had to work. And he came up with exactly the same theory, with a far, far deeper understanding of what it meant. So, it's possible to say that Einstein made only minor contributions to the theory of relativity, just as it's possible to say that Copernicus did nothing but a trivial mathematical transformation of coordinates. But to say that ignores in the most profound possible way the real history of both of those subjects. We'll go on with our discussion of the theory of relativity next time.
Okay. So let's go back to our derivation. I'm going to repeat what he did here, right? But in those with those diagrams that you see right in here, that's not as fancy as his. Okay, so here you go. Here's the light clock. The photon bouncing back and forth between those two mirrors. And we are going to use first principles to determine what happens to the time interval that one observed in one referential and the other observed in the other referential. Okay, that's what we're going to do. And again, I'm going to repeat that, right? It just happens that the difference is that this guy here is going to see this photon traveling in a diagonal fashion, whereas this other observer is going to see the photon traveling in the vertical direction only, up and down. Okay, and the period observed, the period of the photon observed by, period of the clock with respect to referential B. That's what it is, okay? Period of the clock with respect to referential B is going to be 2D divided by C, right? D, and D is 2D. The photon is traveling at the speed of the light, so that was going to be the period of this photon. Okay, I'm going to write down the other one as well, the notes. Use the light clock to find how time behaves with respect to two different referentials, right? So say referential A is at rest with respect to you, and referential B is moving with constant velocity. Referential B has a clock that I call C, lowercase c. Okay. The period of this clock as a light clock C, right? Made of two mirrors and one photon that travel between the two mirrors, right? Every time the photon hits the mirror, hits one of the mirrors, right? Hits the upper mirror. You hear a tick. Similarly, every time the photon hits the lower mirror, you hear a tock, tick tock, just like in the drawing there. The period of this clock with respect to referential B, right, is as a clock made of two mirrors and one photon. And by the way, one more important, made of two mirrors separated by a distance D. By a distance D, right? And one photon that travels back and forth. The period of this clock with respect to referential B is Let's get our equations here. And I'm going to write that down. Period of the clock with respect to B. Right? I'm not going to put a comma there. So that's the notation I'm going to use. Period of the clock with respect to B is going to be 2D divided by C. 2D divided by C. And now we're going to repeat for the other observer, right? Because the clock is moving, right, along the x-axis. So here you go. What that the other guy see? Let's see if I can get that. Oh, here you go. I have the wrong illustration here. Let's see. Okay, this one. Right? So the observer in A is going to see this clock, this light, this photon moving in a diagonal fashion. Half of the period is going to take this long. Okay? So the length from here to here is going to be what? Here is VT and here is D. Right? So let's do that. I'm going to put here aside the period of this clock with respect to referential A, right? Is I'm gonna put here A is gonna be twice the distance that the photon travels with respect to referential A. And this distance is going to be what? Gonna be here. Square root is going to be the hypotenuse of our right angle triangle. Okay, that's what I call LC with respect to A, right? The hypotenuse is going to be VT, V of the clock with respect to A, right? Times T of the clock. I'm going to put that T of the clock with respect to A. And we have to square that. Square it. Oh, not this one. Square it plus square. And then notice that I have TC prime here, C prime A here, and TC prime A here. Okay, that's the period of the clock C prime that an observer in referential A measures. Let's try to combine those two, right? Now I'm going to square here, square here, square here. Square here. Square here. And square here. We're getting there, right? I'm going to pass this term to the left, and the equal sign remains this one. Then I'm going to factor. I'm going to factor 4 and t c prime a, okay? Let's do it this way. I'm going to put here parentheses. I take away this term and this term, take away this term and this term. And what I put it here, I'm putting evidence, just those two. We're not quite there yet, but we're getting there. And now, see, I have T C prime A here, and I need T C prime D on the other side. There's a way to get T C prime B on the other side. How do we get them? How do we get it? Right in here. Okay. I rewrite D in terms of TC prime B. C speed of the light divided by 2. That's what D is. D square, like that. And now we are almost there. Don't forget to square the C. Don't forget to square the 2. And then we square like that. 4 cancel out with 4. And we can solve that for TC prime with respect to A just by dividing the right side by this term. Okay. I'm going to divide the C by the C square by this C square and divide the BB square by C square. That becomes 1, right? And finally, we get our final result. That's the square root right in here. And I no longer have this square. Uh-oh. Didn't go the way I want. Now it should work. Good. And we put the C prime. Okay. Now let's compare. That's what we call the gamma factor, right? That was what Lorentz obtained without the principle, without the postulates of relativity, okay? That was and Einstein arrived at this solution with the postulate of relativity, the speed of the light the same in both referentials. Let's take a look how this term behaves, right? This term here is less than 1. Consequently, this parameter here must be greater than 1. V is always less than C. If this term is less than 1, this ratio is going to be greater than 1. Okay, if gamma is greater than 1, right? We can rewrite that in the following way. Here you go. Period of the clock with respect to A, right? And period of the clock A. Oh, wait a minute, I didn't took out. I gotta take out the square root here, right? Like that. Huh? There's no square there. Gamma is greater than 1. Consequently, the period of the moving clock with respect to referential A, the period that the observer in referential A, the period that the observer in referential A measures for the moving clock is going to be the period that observer in referential B measures for the same clock. Okay, that's what we call time dilation. Time dilation. The neat thing is that on the other way it also applies. Okay, so we can do the same thing. We can repeat everything we did here. Everything we did here for referential, for the referential B, for the here you go, for a clock T in referential A, as seen from someone in referential B. Okay, and when we go through the whole derivation, what did we find? We find that the period of clock C with respect to referential B is going to be greater than the period of clock C with respect to referential A. So it doesn't matter if you're referential A or B. The only thing that matters is that if the clock is moving with respect to you, a clock that is moving with respect to you is going to have a longer period than a clock that is at rest with respect to you. Okay, so conclusion. The period of a moving clock is greater than the period of a clock that is at rest. Of a clock that is at rest. What does it mean? What does it mean? Does it mean? Okay, it means that someone that is at a moving referential ages more slowly because his clock is ticking more slowly with respect to the other referential. Okay, that's what it means. And that's called time dilation. What time is that? 10:49. Let's see, last break was 9:40. So it's time for our break. Okay, do you get the idea? That's how we derive the time dilation. Okay, and C, I want to write that down here. C prime is the clock that is moving with respect to A. C is the clock that is moving with respect to B, right? C prime is the clock that's moving with respect to A. C prime is the clock that is at rest with respect to B and moving with respect to A. And then we do the same thing for the other one, right? C is the clock that is at rest with respect to A and moving with respect to B. Sometimes it's difficult to keep track of all of that in your head, right? Because it's too much information. Okay, so what matters is if the clock is moving or not. And that's and we do have experimental evidence for that. Okay, we do have experimental evidence for that. Okay, one experiment that was performed. Okay, one experiment that was performed with 2 atomic clocks. Okay, they were exactly the same. 2 atomic clocks that were exactly the same. Have the same accuracy, the same precision, had the same accuracy and precision, and kept time equally. Okay. One clock was kept in the lab, and a second clock was taken in a trip around the world inside an airplane. Okay. One clock was kept in the lab. I'll call it clock C. Clock C, and a second clock was taking a trip around the world inside an airplane. Clock C prime. Okay. And by the way, the lab was referential A, right? Referential A. In an airplane, the airplane was referential B. When the plane returned, the 2 times the time recording, the period of time recorded by both clocks, the periods were compared, the periods of time recorded by both clocks were compared, and clock C prime recorded a smaller period, a smaller travel time, right? Travel time, here you go. That's the best way to put that. Recorded a smaller travel time because its period was shorter or was longer. Their period was longer, right? So 1 second in the C prime clock took 2 seconds in the compared to the other clock. Okay, so that's what we have. Let's break. Any questions about that? That's one. That's just one experiment. There's another experiment also involve particles. Okay, and I'm gonna talk about that when we return from the break. 10:55 a.m. to 11:10 a.m. I see you soon. Let's see if you have any questions. Yeah, no questions so far. Okay. So we can age slowly. Yeah, that's right. That's right. But you have to be flying very fast with respect to the speed of light for this time to be measurable, okay? Okay, so I'll see you in 15 minutes. Okay, is there any proof of time dilation? There are several direct proofs of time dilation. Extremely accurate clocks have been flown in jet aircraft. When compared to identical clocks at rest, the difference found in their respective readings has confirmed Einstein's prediction. And there is even papers that they publish out there about this experiment, okay? Let's take a look. This time, practical proof. Let's take a look here. I want to see the actual paper. Our actual paper here. Reference must be this one here. Close. During October 1971, 4 cesium atomic beam clocks were flown on regularly scheduled commercial jet flights around the world twice. Once eastward and once westward to test Einstein's theory of relativity with macroscopic clocks. From the actual flight path of each trip, the theory predicted that the flying clocks compared with reference clocks at the US Naval Observatory should have lost 40 plus and minus 23 nanoseconds during the eastward trip and should have gained 275 plus and minus 21 nanoseconds during the westward trip. There is a difference whether you fly west or east, right? And that has to do with the relative motion of the Earth due to its rotation. Relative to the atomic time scale, the flying clock lost 59 plus and minus 10 nanoseconds during the eastward trip, right? And gained during the westward trip, where the errors are the corresponding standard deviations. Those errors, the errors are those one here, this one here, and this one here, right? The standard deviation is pretty high for this one. It's not that high for this one. That's like 3%. 3%, but this one is very high. I'm surprised that 50 look like 15%. These results provide the unambiguous empirical resolution of the famous clock paradox with macroscopic clocks, right? And that's the reference. Okay. And what was the prediction? That was the prediction. That was the measured for the eastward journey. Okay, the westward journey. That was the prediction from theory of relativity. That was the measured amount value. It is very well within the error, right here. Quote from original paper, let's see. Okay, description of the experiment. I want to see the actual paper. On the world. It doesn't look like they have the actual paper, but that's one experiment. Another experiment that they did. Another experiment that was conducted was a particle physics experiment with muon particles. Okay. Okay, muon particles produced in the lab when they are at rest, they have a lifetime X. However, the same muon particles, when they are entering the atmosphere, the Earth's atmosphere, and by the way, traveling at relativistic speeds are found to last much longer than the muon particles that are at rest in the laboratory. Okay, that's another evidence, experimental evidence of time dilation. Okay, so what we are going to do now, 11:15, right? Let's go a little bit low. Let's see what we're gonna do. Yeah, let's go for another 15 minutes. And let's see, let's do the length contraction now. And by the way, I'm gonna plot that equation that you saw so you have an idea. You know, this equation right in here. I'm gonna plot that in terms against v, okay? The velocity of the referential. We can do that in a rather simple way. Relativity time dilation. B T of C prime with respect to A. To the script, and let's say, and then I'm gonna put also T of C prime with respect to B, right? So let's see it's 1 second. Let's say it's 1 second in the proper referential. We call it the proper referential when the clock is at rest, right? The proper referential of the clock is also and here's gonna be in terms of C. Uh-oh, not the copyright symbol. Okay, now I'm clicking. Here you go. In terms of oh, this one's supposed to be here. Like that. It's gonna be, let's say the period of the clock in the proper referential is 1 second. And we started with the clock at rest. And little by little, we start to increase the speed of the clock with respect to referential A. And the we must raise that to the half power, right? Which is the square root. 1 minus v squared over, let's see how I'm gonna do that. Yeah, I don't need to put divide by c squared, okay? Because the speed is being given in terms of c. So the c that's upstairs cancels out with the c that's downstairs, okay? Let's keep on calculating it, right? As we increase the speed, half the speed of the light is too much. We're going too fast here. We already have a 15% difference, right? But let's cut down to 0.01. Otherwise, it's gonna take two. Otherwise, we're not gonna see the details. 0.01, the speed of the light. Let's put that in terms of kilometers per second. Kilometers per second. Okay. (3,000 kilometers per second). 3,000 kilometers per second is very fast. We have no microscopic object, man-made object has ever reached this speed. The fastest that I'm aware of is 100 kilometers per second, not 1,000 kilometers per second. I'm gonna put here none better. I don't want that many decimal places, but I want the 1,000 separator. Okay, 6% the speed of the light, 18,000 kilometers per second, right? Now look at the difference here. The difference is only 1.4% at this point here. And at 50% the speed of light, 15% difference, right? And as we move faster and faster, this function, it grows very slowly, okay? And then suddenly it blows up. Here you go. Here the speed of the light. Okay, Einstein's theory fails at this limit. Einstein's theory fails at this limit. At this limit, Einstein's theory says that the period of the clock is infinitely long, so infinitely long. So the clock is just as though the clock stops. The clock in the other, the moving clock, right? Just as though the period of the moving, it's not that the period of the moving clock stops. I have to be very clear about that, okay? It is whatever you measure, you that are outside, that far away from the clock, you're the one who's always keeping an eye on that clock somehow, right? You're observing that clock. You see the ticks and tocks of the other clock is slow down. At this point here, at 99% of the speed of the light, okay, the observer on Earth measures 7.09 seconds for every second in his own clock that he's holding. Okay, that's a very important interpretation. You have to grasp this important interpretation, otherwise you won't be able to understand what time dilation is. You have your clock here in front of you. You have this other clock flying away from you, flying at speeds ever faster and faster. And you manage to keep an eye on that clock that's moving away from you. Okay, you compare the period of that clock with your clock, and you notice that that clock is moving, the time is flowing slower. 1 second in your clock corresponds, for instance, to 4 or 5 seconds on the other clock. 1 second in your clock corresponds to 7 seconds on the other clock. That are a speed very close to the speed of the light, right? And you can plot this graph. That's how it looks like. That's how the graph looks like. Ignore those points here, right? I'm going to get rid of it. Here you go. Now we have at the speed of the light, the period of the flying clock increases drastically. We can even go even finer, right? 0.991, right? Like that. 0.991, 992. So you can see what is the resulting, what's the result of your measurement. 93, 94, 95. You know, most of the changes occur very close to the speed of the light. 97, see? 98, 99. Okay, 99.9% the speed of the light. So between 99% and the 99.9%, the variation is huge, right? The change is huge. And we can even plot that here as well, you know. So look, it starts to become perceptible only at 80% of the speed of the light. Let's see. Let's use our this definition of negligible, right? Anything below 10% is negligible. So we're talking about, okay, 0.42, the speed of the light. That's when it's no longer negligible. At 0.42, the speed of the light, you have a difference of 10% of the period of the clock. It's not 0.8, but 0.42, right? So 1 second in your clock that is with you, measures 1.1 seconds in the other clock there. Okay. Okay, so 11:27. Yeah, I think we can stop here. We still have length contraction and the relativistic Doppler effect. Okay, we did length contraction. No, we did time dilation, right? Dilation. Next, we're going to see, we are going to see the relativistic Doppler effect. And that's when we should revisit those sections that we didn't cover before about sound, okay? And the other one is, there's a reason why we do relativistic Doppler effect. There is the regular Doppler effect. There is the regular Doppler effect, by the way, that we are going to cover next time. And there is the relativistic Doppler effect. So the plan looks just like that. Postulates of relativity, the light clock, time dilation. Once we get time dilation, we can show the relativistic Doppler effect, and we can also show the length contraction. But before we get into the relativistic Doppler effect, we're going to cover the regular Doppler effect so you can understand better. And after that, we're going to do the length contraction. This, what you see right in here is just an introduction to relativity, okay? The real theory of relativity starts with the Lorentz transformation. And the plan continues with the Lorentz transformation. Here is just like an introduction to relativity. Here is more like the qualitative explanation of those relativistic effects. When the real explanation starts with the Lorentz transformations that we can derive, not just time dilation, not just the relativistic Doppler effect, not just the length contraction, but much more. Much more. Let me show you the plan here. The Lorentz transformation are far more powerful than the light clock. Here you go. Lorentz transformation, simultaneity of events, time dilation, length contraction, right? And then we have the velocity transformation equations. We have the relativistic linear momentum, the relativistic energy, relativistic kinetic energy, and so on, okay? So let's go for our break. It's 11:31 a.m. The exam 11:31 to 12 noon, right? The exam will become available 1 minute before 12 noon, 11:59. 11:59 a.m. Okay? Any questions?